Hello everyone, welcome back. In this particular video, we're going to focus on the chemistry of esters. And what we're going to do initially is look at the synthesis of this class of molecules. How are these molecules synthesized? Now, all known methods for synthesizing esters, or at least all common methods for synthesizing esters, they are based on carboxylic acids. Carboxylic acid is the starting material for synthesizing this class of compounds. One possibility here is to take the carboxylic acid and then react it with a base. So an example being sodium hydroxide. Since you have an acidic proton here, when you react the carboxylic acid with a base, it will convert the carboxylic acid into the carboxylate ion. Okay, so you get a carboxylate ion, which is the conjugate base of the carboxylic acid. That's what the carboxylate is. And now once you have the carboxylate, if you look at the ester molecule R prime, you have to just add an R prime or the other carbon containing group to this oxygen. So you could simply do an SN2 kind of reaction to make that bond. So you could take the carboxylate, and if you attack an alkyl halide, you would do an SN2 reaction, and that would convert your carboxylate ion into the ester molecule. So notice we make the ester that way. Now, since this last step or the second step here is an SN2-like reaction, what that means is that all the conditions that apply to SN2 reactions, they would apply here. So this reaction would work best with methyl halides or primary alkyl halides. And it's not going to work with tertiary alkyl halides because tertiary alkyl halides are not good substrates. They are not good substrates for an SN2 reaction. Okay, so that's the synthesis. That's one synthesis starting from carboxylic acids. A second approach to synthesizing an ester from a carboxylic acid would involve the acid chloride. So you can convert a carboxylic acid into an acid chloride by reacting it with thionyl chloride. And once you know, once you make this the acid chloride, you can then react it with an alcohol in presence of a base, pyridine being the most common base. Now, sometimes you would notice that a base may not be involved, but excess of the alcohol is used, and that would work fine here too. But the base would make the overall reaction more efficient. Okay, it's going to push the reaction forward. So you could react the acid chloride with an alcohol in presence of a base to again get your ester. So you can synthesize the ester that way. Now, so both of these methods, they start with the carboxylic acid and they convert the carboxylic acid into some intermediate, whether it's the carboxylate ion, which is the conjugate base, or the acid chloride. And then you go ahead and make the ester. The most straightforward and the simplest synthesis of carboxylic acid esters, or esters in general, involves a direct reaction of a carboxylic acid with an alcohol. This reaction is catalyzed by acid, so sulfuric acid or para-toluene sulfonic acid, one of those acids can be used. And this reaction converts the carboxylic acid and the alcohol into an ester. Overall, this reaction results in the loss of a water molecule. So you can view this as a dehydration in some sense. You're losing a molecule of water between the carboxylic acid and the alcohol to get the ester molecule. This reaction, which directly converts the carboxylic acid and the alcohol into an ester, is called the Fischer esterification reaction. What we're going to do next is look at the mechanism of a Fischer esterification. The mechanism of a Fischer esterification starts by an initial protonation of the carboxylic acid molecule. So when you have a carboxylic acid and when you're reacting it with an alcohol, and I'm using para-toluene sulfonic acid, catalytic amount of that acid, we do not need a lot of the acid because the acid would be regenerated in the end. You would get the ester molecule plus water. So the reaction starts by the protonation of the carboxylic acid. Now, like any other carboxylic acid derivative, the carboxylic acid molecule is basic and nucleophilic at the acyl oxygen. So that's what gets protonated. Now what I'm going to do here is, for the purposes of the mechanism, I'm just going to use HA to represent an acid, okay? That's the H, the proton in the acid. So the mechanism starts by an initial protonation. So the acyl oxygen gets protonated using the acid that's in your reaction mixture. And this would give us the protonated carboxylic acid. So the carboxylic acid is now protonated. Okay. Once the protonation is done, the next step in the mechanism is the attack by the nucleophile. Now, relate this to other mechanisms of carboxylic acid derivatives or carboxylic acids that we've seen under acidic conditions. So under acidic conditions, the first step is always a protonation, and then the second step is the nucleophilic attack. So this protonated carboxylic acid now gets attacked by the alcohol molecule. Okay, so the oxygen uses its lone pair to go and attack that acyl carbon. Simultaneously, the double bond here opens up to push electrons to the oxygen atom. And this would bring us to our next intermediate, where we will have the carbon here. What was the acyl carbon would now be connected to two hydroxyl groups. Notice the double bonded oxygen with the hydrogen on it becomes another hydroxyl group. And we would have the alcohol connected to that carbon through using the oxygen atom. And the oxygen would have a formal charge on it. Now, like with any other mechanism, always keep focus on the target. Where are we going? Okay. So if you look at it, to go from this intermediate where we are now to the product ester, what we need to do is we need to deprotonate this oxygen here. We need to remove this hydrogen. Okay, that was R prime. So we need to remove that hydrogen, and then we need to get rid of one of the hydroxyl groups here and put a double bond back. So since we need to deprotonate, the next step here is going to be the deprotonation. And since this reaction is usually done in the presence of excess alcohol, which means you use the alcohol as your solvent for the reaction, what we can do is we can use the alcohol for the deprotonation. The alcohol can act as a base. And again, recollect from SN1 chemistry that the alcohol can serve as a weak base as well as a weak nucleophile. So the alcohol molecule can use its lone pair on the oxygen to deprotonate this intermediate that we got. And it would bring us to the next step where we have OR prime, two lone pairs on that oxygen, have hydroxyl group and hydroxyl group. Now also notice that I'm drawing each step as a reversible step, because if you think about it, each of these steps is reversible. We are protonating the acyl oxygen in the first step, but we will make A minus along with it. Okay, the A minus can go ahead and deprotonate, and it will bring us back to the carboxylic acid. Or when the alcohol attacks, you push up the lone pair, but a lone pair from this hydroxyl can come back down and push out the alcohol. So you can go back and forth. This is just an acid-base reaction, a deprotonation. That's also reversible. So we get to the next intermediate here. And along with this, we will have our protonated alcohol. I'm going to draw it out because we need to use the proton again. So I'm going to draw it as R prime OH one lone pair and positive charge. And now since we need to get rid of one of these hydroxyl groups to get that double bond, what we are going to do is we're going to protonate one of these hydroxyl groups. Again, which one you choose is irrelevant. There are 3 oxygens in this intermediate. In principle, any of these oxygens can get protonated. If the ether oxygen here with the OR, if that gets protonated, that brings us back to the previous intermediate. But when one of these 2 hydroxyl groups get protonated, it will move the reaction forward. So it gets protonated, electrons move to that oxygen again, and this will bring us to the next intermediate here, where we have R, O, R prime, going to have OH, and then an OH2, lone pair, positive charge. So notice what we've done is we've converted one of these hydroxyl groups into a good leaving group. And along with this, we're also going to get our alcohol back from there. Okay. Now we are really close to the end of this mechanism. What happens in the next step here is that the oxygen lone pair can come down from the hydroxyl group. The lone pair can come down, and it can push this water molecule out. And you get to the next intermediate where you would have R, C double bond O, OR prime, hydrogen, one lone pair, and positive charge. We're really close. We are at the protonated ester right now. Okay. Now, what I did here is I used 2 electron pushes simultaneously to get to this protonated ester. And along with this, we are going to release water molecule. That's this water molecule that's coming out over there. Okay. Now, you could, in principle, split this electron push into 2 steps. Okay. So if I draw this molecule again, what we are looking at is OR prime, hydroxyl, and an OH2, positive charge. So let's say if I don't want to push 2 electrons or don't want to show 2 electron pushes at the same time simultaneously, I can split them up. Because we have a good leaving group here, the OH2, okay, the hydroxyl, which has become the OH2, what we can do is we can just say that, okay, this water leaves. That's a good leaving group. Under the reaction conditions, it leaves. And plus this reaction, again, a little bit more detail, this reaction is usually heated. You will do this with heating. Okay, it needs some energy for the reaction to occur. So the water molecule leaves, and this will bring us to an intermediate where we would have OR prime, we'll have hydroxyl group, and there would be a carbocation on that carbon because the water molecule left from here, so there should be a carbocation. And now if you look at this intermediate that we made, if we do resonance on this intermediate, it will take us to this other intermediate that we have. Okay, it will bring us to this other intermediate. And so you could do it stepwise, or you could show the electron push in one step. And essentially from this last intermediate that we have here, if we use an alcohol molecule again, a molecule of alcohol can deprotonate this intermediate, put the electrons down, that would bring us to the ester. So that's the complete mechanism of a Fischer esterification. Important thing to note is that the initial protonation happens at the acyl oxygen, and then the alcohol attacks the acyl carbon. And what you should realize as you work through the mechanism, if you track it, notice that the oxygen that's coming from the alcohol, that is what ends up as the ester oxygen in the product. It stays throughout, okay? It is there throughout and finally becomes the ester oxygen. So the hydroxyl group in the carboxylic acid, in a very broad sense, is what's lost as the water molecule here. Now, since this reaction is completely reversible, every step in the mechanism is reversible, what that means is if you can go forward, you can also come back. That means if you take an ester with water, and if you add acid to it, and if you reflux it, if you heat it, you should be able to hydrolyze the ester and come back to the carboxylic acid and the starting alcohol. Okay, and so that could be a problem as far as the reaction is concerned. So when this reaction is done, the Fischer esterification is done, what you have to do is to push the reaction forward. What you would have to do is you would have to remove the water, okay? Remove water, or you could remove ester, one of those two components, okay? It could be water or it could be ester. You want to remove one of those components so that you can push this reaction forward by Le Chatelier's principle. When one of the products is going to be missing, then the reaction would be pushed forward. Okay, so that's the Fischer esterification reaction, the most straightforward reaction for synthesizing esters, starting from a carboxylic acid and an alcohol. Next, let's look at some examples of Fischer esterification reactions. So I have basically a few examples here to represent like various possibilities here. So let's say in the first example here, we have working with benzoic acid. So it's a carboxylic acid that's based on benzene. You're reacting it with ethanol in presence of para-toluene sulfonic acid, and you're heating it. So under these conditions, carboxylic acid plus an alcohol in presence of acid, that would give you an ester. So the ester product can be written by putting down the structure of the carboxylic acid, draw until the acyl carbon, or the acyl group, sorry, draw until the acyl carbon, skip this hydroxyl group, and replace this hydroxyl group with the oxygen and the ethyl group from here. Or the other way to think about it is remove this hydrogen group and add the carbon containing group that's present in your alcohol molecule, and you would get the structure of the product. Okay, two ways of thinking about it. And I guess the simpler way is to just think about it as replace that hydrogen with the carbon containing group in your alcohol molecule. Important point to note though is that you want to maintain the connectivity in your alcohol. The carbon that's connected to the oxygen in your alcohol, or the alpha carbon in your alcohol, must connect to that oxygen in the ester, but that would be the product that we would get. So that will be ethyl benzoate. That would be our product. The second example over here, I have a molecule which has both a carboxylic acid group and an alcohol group within the same molecule, and we are reacting it with an ester. In this particular case, the oxygen again here, the ester oxygen, if you work on it mechanistically, the ester oxygen would get connected to the acyl carbon in your product. Okay, so if we look at it overall from the acyl carbon to the ester oxygen, we are looking at 6 atoms. So our product would be a 6-membered ring, cyclohexane, that's connected to another 6-membered ring. So starting from here, we have 1, 2, 3, 4, 5, and 6. So that will be our product. So it would give us a cyclic ester, an ester molecule where the reaction happened within the molecule, okay? The alcohol was within the molecule, the carboxylic acid was within the molecule. They basically formed a bond. So you get an ester molecule that's cyclic in nature. The third example here, we have a carboxylic acid, 1, 2, 3, 4. So it's a butanoic acid reacting it with benzyl alcohol. So the product that we get here would be benzyl butanoate, okay? So oxygen here should connect to the alpha carbon of your alcohol. So oxygen connects to the alpha carbon, and there we have our benzene ring. So those are some solved examples of how would you put down or write down the structures of the products from a Fischer esterification reaction. Next, we are going to look at the reactions of esters. One of the first reactions of esters that we're going to talk about is the hydrolysis of esters. This is the reaction of esters with water. And when an ester reacts with water, okay, so when an ester undergoes hydrolysis, what happens is the ester is converted to the carboxylic acid and the alcohol that constituted the ester. Now, the hydrolysis reaction can be accomplished or can be done under different conditions. It could be either acidic or basic. We'll look at them one by one. Under acidic conditions, an ester is reacted with acid, aqueous acid. So that means we have H plus acid and there's water, okay? And with heating. So we can basically represent the H plus and the water by using H3O plus, like a hydronium ion. And so the ester is converted into the carboxylic acid plus the alcohol. Now, notice that this is the reverse of a Fischer esterification reaction that was also done under acidic conditions, and it converted the carboxylic acid and the alcohol into an ester molecule. So the hydrolysis under acidic conditions is just the reverse of a Fischer esterification reaction. We'll look at the mechanism of this reaction, which is basically the reverse of a Fischer esterification reaction. So the mechanism of the reaction starts with an initial protonation or a proton transfer. And like any other carboxylic acid derivative or any other reaction involving carboxylic acids, the proton transfer or the protonation occurs at the acyl oxygen. The acyl oxygen is what gets protonated. So in presence of an acid, the acyl oxygen gets protonated. So electrons are pushed up to that oxygen. And we will get the protonated ester molecule. So we get the protonated ester where the acyl oxygen has been protonated. And along with this, we make water. And realize this reaction is going on under aqueous conditions, so there is enough water around. Once you get the protonated ester, the second step here is the attack by water on the protonated ester molecule that opens up that pi bond or the double bond onto the oxygen atom. And it would give us a hydroxyl group here, give us a water molecule that's connected to that carbon, has a formal charge on that oxygen, and there is OR prime group here, okay? So the R prime. Now, if you look at the products, what we need to do is we need to break this bond between that carbon, the acyl carbon and the ester oxygen. We need to break that bond. And so we'll have to like protonate it at some point. But right now, the most immediate thing that we're going to do in the mechanism is to deprotonate this. So again, under these reaction conditions, water would be the most ideal base that's present here. So a molecule of water, another molecule of water can deprotonate that hydrogen. So electrons go to that oxygen and we get a molecule where there are two hydroxyl groups connected to it, and then the OR prime. Now, if you go back to the mechanism of Fischer esterification, you would notice that we arrived at a similar intermediate in that mechanism also. In fact, all of these intermediates should bear some resemblance to what we saw in the Fischer esterification mechanism. Okay, once you're at this intermediate, along with this, you've made acid again. So the hydronium ion is regenerated, and now any of these oxygen atoms in this intermediate can get protonated. If the hydroxyls get protonated, they bring us back. But whenever this oxygen, the ester oxygen, gets protonated, that takes us forward in terms of the mechanism of the reaction. So it will take us to the next step where we have RC hydroxyl group, OR prime, OR prime, and there is a hydrogen here, one lone pair and one positive charge. And at this point, the the alcohol, the protonated alcohol that we've created here, that can be pushed out. It is a good leaving group. Okay, we've converted the bad leaving group, which is an alkoxy group, into an alcohol good leaving group. So one of these oxygens, the hydroxyl oxygens, would push down its lone pairs, and that would assist in the loss of this alcohol group. So those electrons come down and the alcohol is lost. So it will bring us to the next intermediate, where we have R, we have C double bond O, OH with a protonated acyl oxygen. And along with this, we will have the alcohol molecule. So we've created the alcohol molecule now, the R prime OH. And in the last step then, in the last step here, another molecule of water, which is present in excess here, that can come and deprotonate this oxygen to give us the carboxylic acid plus H3O plus. So if you notice, overall, we've converted the ester into a carboxylic acid and the alcohol, so the products that we've drawn here. And we've added overall like a molecule of water in that process. So that's the mechanism of an ester hydrolysis under acidic conditions. Next, we're going to look at hydrolysis under basic conditions. So under basic conditions, the hydrolysis of an ester is done in two steps. You initially react the ester with a base. I'm using sodium hydroxide, a very classic base here. And so when you do this reaction, the ester reacts with your base to give you a carboxylate ion and then an alcohol. And then in the second step, you do a hydrolysis, like an acidic workup actually. So an acidic workup here. And when you do that reaction, you convert this carboxylate ion into the carboxylic acid, and the alcohol was already there. So to convert this carboxylate into the carboxylic acid, an acidic workup is needed, or a protonation step is needed. Let's look at the mechanism of this reaction. Now, since this is a reaction that's going on under basic conditions, the mechanism would resemble the mechanism of or the reactions of carboxylic acid derivatives under nucleophilic or basic conditions here. So let's work on the mechanism here. So the mechanism starts out with the attack by the nucleophile on the acyl carbon. So there is no protonation here. There is no initial protonation. The mechanism starts out by the attack of the nucleophile here, which is your hydroxide, on the acyl carbon. Attacks the acyl carbon, the double bond here is pushed up, and that would give us RC minus with a hydroxyl group to it and an OR prime. So you get the tetrahedral intermediate, okay? That's the tetrahedral intermediate. And from the tetrahedral intermediate, you can now get the collapse of the tetrahedral intermediate. So the negative charge comes down, and as it comes down, in principle, it can push out the hydroxyl group here as a hydroxide, and that would bring us back. Or it could push out the alkoxide group. That would take us forward. So we will get the carboxylic acid, okay, the C double bond O, OH, plus you're going to get R prime O minus. That's an alkoxide, okay? This oxygen here, that becomes the alkoxide. Now at this point, if you notice, we have the carboxylic acid and the alkoxide, but the carboxylic acid is more basic than the carboxylate, okay? So what happens is once you get here, so there is an acid-base reaction and the alkoxide deprotonates the carboxylic acid to give us the carboxylate ion plus the alcohol. So all of this happens in step one. And that's why at the end of step one, you end up with a carboxylate ion and an alcohol, because this acid-base reaction is favored in the forward direction. So it's not so favored in the backward direction, because the carboxylic acid is a stronger acid compared to the alcohol here, or the alkoxide is a stronger base compared to the carboxylate, okay? Either ways, it is favored in the forward direction, so you end up with the carboxylate ion. And so that's why when we do this second step, which is the acidification, okay, or we do an acidic workup, now the carboxylate gets protonated so that we get a carboxylic acid molecule here. So we generate the carboxylic acid that way. We have already generated the alcohol. So in the end, essentially, we have the carboxylic acid plus the alcohol. This basic hydrolysis of an ester, okay, or the hydrolysis of an ester under basic conditions, is also called a saponification reaction. It's called the saponification reaction. And that's because this reaction is used to make soaps, or it was used to make traditional soaps starting from vegetable oils. We're going to draw that scheme next. Soaps were traditionally synthesized by the saponification reaction of esters. But these esters are specific molecules. They are triglycerides, okay? These are the molecules that make up vegetable oil or animal fat. So the molecule of vegetable oil or animal fat looks like this. Now it's drawn in a very weird way, sort of, but if you look at it, there are 3 ester groups in this molecule, okay? So it is basically a molecule with 3 ester functional groups, and the alcohol that is here is glycerol. That's why these are called triglycerides. So when you take triglycerides, which are basically vegetable oils or animal fats, and you react them with sodium hydroxide as a base, excess of the base, because we have 3 ester groups here, what happens is you end with the alcohol here, okay, which is glycerol. You get glycerol. So each of these is a carbon, okay? This is a bond line structure for that molecule, essentially. You could draw it differently, but you have 1, 2, 3 carbons with a hydroxyl group on each one of them. That's glycerol. plus, under these conditions, as we saw, we get the carboxylate ion. So you're going to get 3 molecules of carboxylates. And since we are using sodium hydroxide, these would be sodium salts. So even here, we are using sodium hydroxide. So this carboxylate would have a sodium ion attached to it or bonding to it with an ionic bond to it. Okay, what's specific or what's special about these esters is that the R group here, okay, this R group is a long carbon chain, okay, and depending on the oil or the fat that you're using, they could be 10 carbons or longer. Up to like 20, 22, 24 carbons, okay, depending on what vegetable oil or animal fat you're using. Now, for some of the more common vegetable oils, so for example, olive oil or like palm oils, these carbon chains or the R group here, that can be total of like 15 or 17 carbons, because they usually have about 16 to 18 carbons, and that includes this carbon, the acyl carbon. So the R group itself is about 15 to 17 carbons. But these molecules, sodium salts of these carboxylic acids, these are used as soaps, or at least traditionally, these were the soap molecules. Now we have other methods which allow us to make soaps, but they still maintain a similar structure or like some similarity with the structure. Okay, so the saponification reaction is useful for making soaps, a direct application of this chemistry here. Next, we are going to look at the reaction of esters with hydridic reagents or hydride reagents, like lithium aluminum hydride. When an ester is reacted with excess lithium aluminum hydride followed by an acidic workup, our product is an alcohol. In fact, we make 2 alcohols here, okay? And I'll walk you through that. Why? Okay, so essentially what happens in this reaction is the acyl carbon here, that is reduced, okay? That's the reduction. The carbon-oxygen double bond is gone. So that's reduced to an alcohol here. So the acyl carbon becomes the alpha carbon for one of the alcohols, but the ester has another alkoxy group in it. That comes out as the second alcohol. So overall, you're getting 2 alcohols from this reaction. Now, most often and very often, you focus on the alcohol that's coming from the acyl part of it, because the other molecule here was already very close to an alcohol. So the reduction is for the acyl carbon. Let's look at the mechanism of this reaction. It is very similar to the reaction of lithium aluminum hydride with acid chlorides and acid anhydrides. So the mechanism starts with an initial attack by lithium aluminum hydride on the acyl carbon. So we're going to use aluminum hydride here. So one of these nucleophilic hydrides goes and attacks the acyl carbon. The double bond gets pushed up. And again, this is a nucleophilic reagent, so our mechanism resembles the reaction of carboxylic acid derivatives, or resembles the nucleophilic acyl substitution under nucleophilic or basic conditions. So the first step is an attack. Electrons move up, so we get our carbon with a single bond to an oxygen. We have OR prime, and we've got a hydrogen on that carbon. And along with this, we are going to have our aluminum, okay, with the 3 hydrogens on it. Now, after this, like any other nucleophilic acyl substitution reaction, this is our tetrahedral intermediate. So the tetrahedral intermediate collapses, the oxygen brings down its lone pairs, and at the same time, the alkoxide group here is kicked out. That leaves. Now, hydrogen is a very bad leaving group, so that does not leave in this particular step. And this takes us forward to the next intermediate, where we're going to have an aldehyde, KRC double bond O with an H, plus we have an R prime O minus, an alkoxide that came out, okay? So this is one of the alkoxides that we made in this process. We're going to leave it there, but we're going to track it later. Now, we have excess lithium aluminum hydride, and what we know is that aldehydes also react with lithium aluminum hydride. So the reaction doesn't stop. In fact, if you try to stop it at the aldehyde, it would not work. You will get a mixture of products. So it's better to just let it continue on. So this reacts with another molecule of the hydride. The hydride comes and attacks now the carbonyl carbon, okay? We started with an acyl carbon. Now we have a carbonyl carbon. So the hydride from the lithium aluminum hydride comes and attacks the carbonyl carbon. That will bring us to this intermediate, which is notice another alkoxide. Okay, so we made another alkoxide here. So this is alkoxide 2. Number 2, alkoxide number 2, along with we have the aluminum reagent. Now, in principle, okay, you can use all 4 hydrides in the lithium aluminum hydride, but for the sake of mechanism, we're showing separate aluminum hydrides to work through the mechanism here, okay? So that's basically the first step. And notice, by the end of this first step, we have 2 alkoxides in our reaction now, okay? We have alkoxide 1, which was present in the ester, so that's the OR group in the ester, and we have alkoxide 2, which is from the acyl carbon. So this carbon here is the reduced acyl carbon. And now, when we do the acidic workup here, okay, when we do the acidic workup, the alkoxide here will get protonated, but there is enough acid simultaneously that other alkoxide is also going to get protonated. So when we do this reaction, at the end of it, we're going to have 2 alcohols in our reaction. We'll have alcohol from alkoxide 2. We will also have the alcohol from alkoxide 1. Okay. Now, like I said earlier, in most cases, you track the alkoxide that's coming from the acyl carbon, because that's the carbon which is reduced. So that's the one that we usually focus on. Let's look at a quick example here. So let's say if we have an ester like that, methyl benzoate, if we reduce it with lithium aluminum hydride excess, followed by an acidic workup, we will get 1 alcohol from this alkoxide in the ester, or the alkoxy group in the ester, and we're going to get another alcohol that corresponds to this acyl carbon. So our reaction will give us 2 alcohol products. One will be benzyl alcohol. This carbon, the acyl carbon, is reduced to an alcohol, and plus it will give us methanol. Now, since we are doing a reduction here, the benzyl alcohol here, that would be considered our reduced product. Okay, we are not doing a reduction as far as this methoxy group is concerned. So we're not doing a reduction as far as the OR prime is concerned. We're doing a reduction of the acyl carbon. So this would be our main product. Okay, that's something important to keep in mind. So we looked at the reduction using lithium aluminum hydride, which helps us convert esters into alcohols, or the acyl carbon in an ester into an alcohol carbon. What if we wanted to stop at the aldehyde and not go further? How would we do that? We're going to look at that next. Now, a reagent that is useful in converting an ester to an aldehyde, and again, I want to mention that when we say ester to an aldehyde, we are referring to the acyl carbon. That's what we are focusing on. So if you look at the scheme here, the acyl carbon, which is a carboxylic acid derivative here, okay, is converted into the aldehyde here. So to convert an ester to an aldehyde, a reagent that's useful is DIBAL-H, okay? DIBAL-H, which is diisobutyl aluminum hydride. This is the structure of DIBAL-H. So there are two isobutyl groups on the aluminum along with one hydride. The mechanism of this reaction is very similar to that of a lithium aluminum hydride mechanism, except that you will use DIBAL-H instead of the aluminum hydride. But the advantage to this reaction is that if you react an ester with DIBAL-H, this reaction is done at low temperatures. Okay, so that's important. If you do this reaction at low temperatures and you follow it up with an acidic workup, you're able to isolate the aldehyde. You can stop at the aldehyde without over reduction to the alcohol, because with lithium aluminum hydride, what happens is the aldehyde product gets further reduced to the alcohol. So we are able to avoid that reduction here and isolate an aldehyde. Again, notice that the alkoxy group in the ester here still becomes an alcohol, but that is not what we're focusing on. We're focusing on the acyl carbon. We're talking about the reduction of the acyl carbon, and the acyl carbon here, which is a carboxylic acid-based carbon, is only reduced as far as a carbonyl compound. So we can stop at the carbonyl compound. So depending on what you want to do with the ester molecule, whether you want to reduce it completely to an alcohol or to an aldehyde, or you want to stop at the aldehyde, you can choose an appropriate reagent. If you want to reduce an ester completely to an alcohol, you use lithium aluminum hydride. If you want to reduce the ester to an aldehyde, you would use DIBAL-H. Those are the two reagents that make these reactions possible. The reaction of esters with organometallic reagents, specifically a Grignard reagent, is very similar to those of all other carboxylic acid derivatives. When an ester reacts with a Grignard reagent and you use excess of the Grignard reagent followed by an acidic workup, what happens is the ester, again, we're talking about this acyl carbon in the ester molecule, that gets converted into a tertiary alcohol. We get a tertiary alcohol here. And plus, the alkoxy group becomes another alcohol group as usual, but we're focusing on the acyl carbon. So the acyl carbon here becomes the tertiary, the alpha carbon in the tertiary alcohol. It gives us a tertiary alcohol. The mechanism here is very similar to the mechanism of the Grignard attack on an acid chloride or an anhydride, which goes through the intermediacy of a ketone. So you first convert your ester into a ketone, and then the ketone is further reacts with the Grignard reagent to give you the tertiary alcohol following the acidic workup. Let's look at an example of this reaction. So if we start with an ester, and again, I'm going to use methyl benzoate here as an example. If we take methyl benzoate and if we react it with ethyl magnesium bromide, an excess of it followed by acidic workup, the acyl carbon here is going to become the alcohol carbon. So we'll still have the benzene ring, acyl carbon becomes the alcohol carbon, and we'll have two ethyl groups connected to that carbon. So that gives us the tertiary alcohol product, along with this methoxy group here becoming the methanol. But our focus here is on the acyl carbon, so that gets converted into the tertiary alcohol here. So that's the reaction of esters with Grignard reagents, which helps us convert an ester into a tertiary alcohol. I hope you find all of these reactions and the discussions useful. Bye.